Getting started with artificial intelligence development requires more than just a powerful computer. It demands a carefully orchestrated setup of software, libraries, and efficient configurations. This journey, from installation of essential tools to fine-tuning your environment for optimal performance, transforms your computer into a robust platform for AI experiments and deployment. To illustrate how you can achieve this, let's delve into each step, providing a practical example as we proceed. The foundation of any AI project hinges on the frameworks and libraries you choose. Among the most popular and widely supported are TensorFlow and PyTorch. Both frameworks offer expansive capabilities for machine learning and deep learning tasks, valued for their flexibility, rich ecosystems, and active community support. Consider the example of preparing your system for a project that analyzes and classifies images of handwritten digits using deep learning. TensorFlow and PyTorch both provide essential tools for this task, including neural network modules, data loaders, and GPU acceleration. Let's begin by introducing what makes these frameworks special. TensorFlow, an open-source project developed by Google, has become synonymous with large-scale machine learning workloads. Its ability to deploy models for production, versatile modeling capabilities, and integration with hardware accelerators make it a popular choice. PyTorch, developed by Facebook's AI Research Lab, is favored for its dynamic computational graph and Pythonic interface, appealing especially to researchers and those seeking a more flexible approach to model development. Before you install any framework, however, it is crucial to ensure your environment is ready. This step not only prevents conflicting dependencies, but also protects your project from the chaos of incompatible libraries. The best way to achieve this is by using a virtual environment. On Windows or Unix-based systems, Python's built-in venv module or the community-supported virtual env tool can create isolated environments. Alternatively, Anaconda, a distribution that bundles Python and numerous scientific libraries, is particularly popular for AI projects thanks to its seamless handling of dependencies. Start by installing or updating Python. Ideally, use Python 3.8 or newer. With Python in place, create a new virtual environment. For example, on the command line, you might enter Python venv. Activate your environment using the appropriate command for your operating system on Windows. inv activate. On Mac OS or Linux, a source env activate. Now, with the virtual environment running, you have a clean slate for your AI project. Next, install the AI frameworks themselves. Let's focus on the installation for both TensorFlow and PyTorch, making sure to enable GPU acceleration if your system has a compatible NVIDIA graphics card. For TensorFlow, the official recommendation is pip install TensorFlow. If you want to leverage GPU acceleration, ensure your system has the correct NVIDIA CUDA and cuDNN versions installed. Usually, the TensorFlow website provides a compatibility table indicating which CUDA and cuDNN versions are required for your version of TensorFlow. For PyTorch, the process is just as straightforward, but involves additional customization to match your system. Visit the official PyTorch website and use their installation selector. For an example command, it might look like pip install torch vision torch audio index URL https download.pytorch.org/WHL/Q11-8. This command tells pip to install versions of PyTorch, Torch Vision, and Torch Audio that are compatible with CUDA 11.8. At this point, your core deep learning tools are available in your isolated environment. But for most real-world projects, you'll need additional libraries for data manipulation, visualization, and utilities. Popular additions include NumPy and Pandas for data management, Matplotlib and Seaborn for visualization, and scikit-learn for traditional machine learning algorithms. Install them using pip install NumPy Pandas, Matplotlib, Seaborn, scikit-learn. This forms a standard stack, enabling you to load, manipulate, visualize, and model data from end to end. Now, let's return to our example. image classification of handwritten digits using, for instance, the MNIST dataset. Both TensorFlow and PyTorch have built-in utilities to download and pre-process this dataset, making it an ideal starting point for beginners. For PyTorch, you might use the following. From TorchVision import datasets, transforms. Train dataset equals datasets. NIST root data, train, true, download, true. Transform, transforms to tensor. With the libraries installed and your environment prepped, it's time to optimize your setup for performance. Deep learning is computationally intensive, especially when training large models, so fine-tuning your software and hardware configuration yields substantial benefits. The first aspect of optimization is ensuring all hardware drivers are up to date. For those with NVIDIA GPUs, regularly update both the graphics driver and the CUDA toolkit. Visit the NVIDIA website to download the latest drivers compatible with your card and operating system. The CUDA toolkit and QDNN can be obtained from NVIDIA's developer portal. Once installed, verify that your GPU is accessible from your AI frameworks. In Python, you can run for TensorFlow. Import TensorFlow as TF. Print GNOME GPUs available by len tf to config list physical devices GPU. C. For PyTorch. Cut. Import Torch. Print CUDA available. Torch to CUDA is available. If these commands return positive results, your system is ready to offload computational workloads onto the GPU, greatly accelerating training. System monitoring is another vital aspect. As you train larger models, it's easy to overtax your memory or generate thermal issues. Use tools like Task Manager on Windows or HTOP and NVIDIA SASME on Unix-based systems to track CPU, GPU, and memory usage in real time. NVIDIA SMI, in particular, is a command line utility bundled with the NVIDIA driver, allowing you to observe GPU usage, temperature, and memory consumption. Launch it by simply entering NVIDIA SMI. Running this command while your model trains will show a live snapshot of GPU activity, helping you identify potential bottlenecks or instances where your GPU is underutilized. Fine-tuning configuration files can further refine how your frameworks interact with your hardware. Both TensorFlow and PyTorch permit you to limit GPU memory consumption or control which GPUs are visible to your program. In TensorFlow, for instance, you can restrict your process to a specific GPU. Import TensorFlow as TF. tf.config list physical devices GPU. tf.config set visible as GPUs Gmon. Similarly, in multi-GPU servers, you might want to only use a subset of GPUs for experimentation. Import OS. OS environment visible devices. But these adjustments are invaluable in shared environments or when balancing workloads across multiple experiments. Next, dive into the configuration of your chosen deep learning framework for further performance improvements. For example, TensorFlow allows mixed precision training, where computations use a combination of 16-bit and 32-bit floating-point arithmetic. This can double the throughput of your GPU without sacrificing model accuracy in many tasks. Enable mixed precision in TensorFlow as follows. From TensorFlow, Keras, import mixed precision. Mixed precision.set, global policy, mixed float. PyTorch supports similar optimizations with its automatic mixed precision (AMP) feature, which can be toggled during training loops. Simply wrap your forward and backward passes with PyTorch's AutoCast Context Manager. Now, let's see an example that ties all these concepts together. A practical demonstration of a full software setup and an optimized environment for image classification with PyTorch. Suppose you plan to train a convolutional neural network, CNN, on the MIST dataset. Your steps might resemble the following. 1. Set up your environment. Create a Python virtual environment. Install the latest versions of Python, PyTorch with GPU support, TorchVision, NumPy, Pandas, and Matplotlib. 2. Update your drivers and CUDA libraries. Download and install the latest NVIDIA GPU driver. Match your CUDA and QDNN versions to your installed PyTorch version, as advised by the PyTorch website. 3. Verify your environment. Run a test script to confirm the GPU is accessible via PyTorch. 4. Configure your GPUs. If you have more than one GPU or are sharing resources, use environment variables or programmatic configuration to select the proper device. 5. Enable performance-enhancing features. Use torch.cuda.amp for mixed precision training during your model's learning cycle. 6. Monitor your system. Open a terminal to run NVIDIA SMI during training, ensuring your GPU memory and compute are in the optimal range. 7. Implement the model efficiently. Write your data loader pipelines with sufficient prefetching and use pinned memory for faster host-to-device data transfer. 8. Repeat and refine. Profile your training runs using PyTorch's built-in profiler or external tools to pinpoint bottlenecks. Adjust your batch sizes, data augments, or distributed training strategies as necessary. Through this sequence, you have not only prepared your system with the best-in-class frameworks, but you've also built efficiencies into every phase of the workflow. From selecting and fine-tuning libraries to managing dependencies and exploiting hardware acceleration, these steps equip you to maximize output on any AI workstation. In conclusion, setting up software for AI is both a technical process and an exercise in continuous optimization. By adopting best practices, such as using virtual environments, meticulously updating drivers, and making full use of framework configuration options, you pave the way for smooth experimentation, reliable results, and scalable production deployment. Remember that investing time in your setup pays dividends, not simply in raw computational speed, but in the confidence that your AI environment is robust, portable, and ready to tackle the toughest challenges in artificial intelligence.